So 3-second break is over. The next one is humidity. And that is a measure of the moisture in the air. And the most important determiner of the moisture that can be in the air is the temperature of the air. The warmer the air, the more moisture it can hold by a lot. So, for example, you're in Antarctica. Antarctica is like a desert. It's an ice desert, but the ice is accumulated over many, many thousands of years. It doesn't snow there very often at all. There's no moisture in the air. Where the heck would it come from? The air's so cold it can barely hold on to any moisture. And uh, that is partly because of the wind patterns and the movement of moist air. If you're in the mountains that are equally, or maybe not equally, but mountains that are extremely cold, you go up into the Himalayas or something near Mount Everest, and the air gets very dry up there as well. But as that moist air moves across the continent from the oceans and up the mountains, it's getting colder and colder and colder. And so it starts to lose that moisture as snow or rain, depending on the temperature of that um, air at the time. And so the colder the air gets, the less it can hold. And it's a dramatic difference. You can have hardly any moisture in cold air. You can have tons of water um, in very, very warm air. So you're in Florida and it's 96 degrees out, and it might feel like it's 110 because it's just so wet in the air that your body can't get rid of heat. We get rid of heat through evaporation in our skin, and we can only evaporate our sweat. We can only evaporate water and cool ourselves down if there's room in the air to evaporate more water. And you're down in the South in Louisiana, Florida, Georgia, uh, when it's really humid and it feels much hotter because the humidity is so high. In Arizona, for example, you're down in Yuma or Phoenix, and I've been out there on some days. It takes a little adjustment, but I've been out there on some days where it's 110, and it's hot, no question about it. But the body can cool off, especially if uh, you have a little bit of shade. You're not in direct sunlight. Um, the air's typically much drier. It can get humid there, but that's not as common. And because the air is drier, you're constantly evaporating water. That evaporation process takes away heat and it cools you down. So that's important when we think about greenhouses. We use humidity controls to partially manipulate the temperature in the greenhouses. We can use water to cool our crops down. We can use sprinkler irrigation in some situations to make things moist. So as it gets hot during the day, those beds that are moist are going to be drying out. They're going to be evaporating and cooling your crop down, reducing heat damage. Uh, as water is evaporating from the plant's leaves themselves, it's really, really important that the water that was inside the plant just moments ago exits the plants through a process called transpiration. Plants transpire. Humans, we perspire. It's similar body water that's inside of us exits through pores on our skin, and we call that perspiration. Well, there are different kinds of pores. These pores on plants are generally mostly on the undersides of leaves, and we call those little pores the stomata, and they're open and closed by guard cells. And what's really important for that is not only does it help keep things cool when plants are losing moisture, but anytime plants are losing moisture at the leaves, they have to pull up more moisture in the roots. And that's a good thing. People think sometimes, like, wow, all that water's being lost. And that's a waste of water. We water the plants, water goes right through the plant and evaporates through the leaves. If we could stop that evaporation, we could reduce the amount of water used in the production of our crop plants. Eh, wrong. The problem is that constant flow of water from the soil into the roots, up the plants, out the leaves, transpiring as water vapor into the atmosphere is a constant freeway of water containing nutrients. You turn off the flow of water to conserve water, and the plants aren't able to keep moving nutrients from the soil into the plant to grow the plant. You need water movement, you need transpiration, you need water to keep going through. Now, theoretically, you could have an enclosed indoor environment where the water transpires from the plant's leaves, and then you have a condenser unit of some sort to turn the humidity in the air back into liquid water, put it back into the soil or the hydroponic production, and you could reclaim that water. But that's really energy intensive and difficult. We're not there yet, at least not mostly. Um, we can do that in small scale, slow growing things. There's totally enclosed little greenhouse bottles. They recycle the water like that all the time, and they can stay enclosed for decades in some cases. But to do it in high production uh, food crops, no, not yet. So, anyway, what is our atmosphere actually made of? Mostly nitrogen gas, N2. It's two nitrogen atoms joined together into one nitrogen molecule, N2. And that N2 is an inert gas. It doesn't react well. And the only things that can turn N2 gas into usable nitrogen for plants and animals are certain kinds of what are called nitrogen fixing bacteria or lightning or humans that do fertilizer production or something like that. Otherwise, nitrogen in the air, I'm breathing mostly nitrogen. I think it's what, 78%, I think, nitrogen gas, and I can't use any of it. It's just nitrogen. Oxygen is highly reactive. Oxygen burns to create fire, and we can low temperature burn it to utilize sugars and make our cells alive, not only in our bodies, but plants burn sugar in a low temperature chemical reaction with oxygen in the cells of all plants. Bacteria do it, fungi do it. Burning of oxygen is quite normal. And there's lots of other minor gases, but the vast majority are nitrogen and oxygen. And there's also water. And I've mentioned already the amount of water that atmosphere can hold completely depends on temperature. So we call it not water content or atmospheric water content, we call it relative humidity. What is the percentage of moisture that is in the air compared to the percentage that that air could hold at that temperature? So the amount of moisture in the air at 50% humidity when it's really cold out in the morning is much lower than if I had 50% humidity in a hot afternoon. There's way more water in a 50% humidity atmosphere when it's hot out at 50% humidity compared to a cold morning, 50% humidity. So it's relative. It's relative to the temperature, and it's based on a percent. And when you hit 100%, we call the atmosphere saturated. and that is the dew point. And so don't have a glass with any ice in it right now. This is actually a a plastic mug that doesn't form dew on it. But if this was glass and I had ice in this glass rather than just warm iced tea left over, you would get condensation on the outside, wouldn't you? Droplets of water would form on the outside of this cold glass. Why does condensation form? Well, it's warm in my room here, and there's quite a bit of water vapor. I don't know, the humidity might be in the 50% range inside the house, or 40% right now. I'm just guessing based on previous experience. Uh, this time of year, this condition, heater going, it's probably in the 50% range. But it's also about, I don't know, it's probably 70 degrees in this room. What is the temperature of a glass filled with iced tea and ice? It's going to be close to 32, 34 degrees, right? It's going to be really cold because of the ice and the water in the glass. So as the moisture in the air hits that glass and the air gets cold right next to the glass, and that thin layer, that last millimeter of air that's just around the glass gets really cold. The air gets cold next to the glass. And as it gets cold, it can't hold on to its water anymore. So the 50% humidity in my room becomes 100% humidity when it touches the glass. Because the air got cold, it can't hold on to that moisture anymore. Where's that going to go? It's not going to form a cloud and start raining in something that small, but it can settle out water directly on the glass. That's how the condensation forms on your glass of iced drink. And the same thing happens at night. It gets warm during the day, the moisture moves in off the ocean here, and there's a lot of moisture in the air, and it's 62 degrees in the early afternoon, evening, and it gets dark, and it's now 52, and then it's 47, and by the time early morning hits, maybe the temperature's gone down enough to cause the humidity to go up to 100%. And dew starts to form. And so you get drops of water forming on various substances. And it's not all even. Some things hold on to residual heat, so you don't get dew typically on big rocks and concrete. You get it on grass blades. You get it on the glass on your car windshield. Things that cool down faster and help force more of that air to cool down right in that area and cause dew to form. So how do you measure it? Now, this is one I wish I was in class. It's always fun to do a sling psychrometer, as it's called. You take this little pivot handle, you hook it into the end, and you can see here there's two thermometers, not just one, two thermometers. And on the end of one of the thermometers, you have this little cotton sock tied on very carefully onto the bulb of the thermometer. The other one is called the dry bulb. And on the wet bulb, you either dip it into your canteen or you spray it with a water bottle, whatever. You need to get it soaking wet. And then you hook the handle to this little eyelet here, and you hold it over your head and you go woohoo for 2 minutes, a big lasso. When I was a firefighter, I had one of these. I had one on my belt that I would keep with me at all times. I was a wildland firefighter. Instead of a little chain, I actually had a leather strap, and I would lasso it and just be swinging it for 2 minutes. And 2 minutes takes a lot longer than you think when you're doing this over your head. But what happens? The dry bulb, there's no evaporation happening. So the dry bulb is just measuring the air temperature. The wet bulb is going to get colder. Maybe. Because what do we have here? A wet sock. as I'm spinning it around over my head for a couple of minutes, if the air isn't saturated at 100%, there is going to be a little bit of evaporation off of that sock. It's going to start evaporating. The water's going to turn to gas because I'm swinging it in the air. What does evaporating water do? Cools things down. So maybe if it's, 73 degrees, the number just popped into my head somewhere. If it's 73 degrees in the air, but I'm swinging this thing around in my head and I look at the dry bulb and see 73, the wet bulb, what if it's 63? That means there was 10 degrees of cooling due to evaporation. And then you just look it up on a table. And I had a plasticized, waterproof table that I also kept on that little thing on my belt. It was a wildland firefighter thing, so I was loaded up with all kinds of stuff. But I would often have to report to my boss what is the humidity and what is the temperature. And a sling psychrometer is a great way to do it. And there are other devices called hygrometers, and it's with a G, hygrometers. If you've taken soil science, maybe you remember that little floating device in our measurement of soil texture, and we had to float this little device that would slowly sink over an hour. That's a hydrometer with a D. It measures the density of liquid solutions, hydrometer with a D. Hygrometer is a different device for measuring relative humidity using a different concept. And I won't get into the details. People used to measure relative humidity using specially calibrated horsehair materials. And there's a lot of ways to do it. I mean, horsehair, what happens when the air is really humid? The horsehair relaxes, and so it stretches a little bit. And when the air is dry, the horsehair shrinks a little bit, and you can actually get a really accurate measure. They don't last for a long, long time, but several years you can get a good, accurate approximation of relative humidity using nothing but horsehairs. That's what they did in the old days. Now we have really accurate ways. This sling psychrometer is my favorite because there's nothing to go wrong as long as you've got good quality thermometers and you double check them every once in a while that they're measuring accurately. They're beautiful. The dew point, already talked about that. It's when the relative humidity rises as the air cools. And at some point, when the air gets colder, 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 you'll hit 100% saturation. That's the dew point. So you have a drink. I've already described this. Droplets on the outside of a glass or condensation on the outside of a glass, or dew on the grass out in the front of your house or on the windshield of your car in the morning. So here's one of those measuring devices that I kept in my pocket or my little leather pouch on my belt. And it looks a little complicated at first. You don't have to worry about how it's organized. I'll explain it briefly, but it will not be on a test. You can see the dry bulb temperature is in this lighter blue color. So here, this is 95 degrees, nice hot day. The wet bulb temperature, and you measure it 60, 70, 80. So here it's 70 degrees. So 95 dry bulb, 70 wet bulb, and the relative humidity, you follow this arc. And I can't even see. I'm not even going to try to see. Well, I guess I can. 30, 40, 50. Should be wearing my glasses for this. But it looks like we're maybe around 28%. I'm just guessing. And where's the dew point? I can measure over from this to figure out what my dew point is. It's 57 degrees, so I could figure out how cold would it have to get for that atmosphere to start a dew point, and then the HR ratio, which I won't even talk about. Um, but the um, the important things that I needed to know was the percent humidity, the air temperature, and depending on what was going on, the dew point, because the plan on a fire would be really important to know if it might get cold enough to give us a hand with a dew in the area that would slow the spread of the fire. And from an agricultural standpoint, do I care about fire suppression? No. From an ag standpoint, I cared about it again. Now I care about this dew point because that is when my leaves get wet. That is when I have concern with bacterial and primarily fungal diseases. There's all kinds of disease modeling that are based on hours at the dew point. It's the leaf wetness calculation. And without ever going out in the field to see if your leaves are wet, you can collect weather data to determine how much leaf wetness your plants experienced in the field. And the more leaf wetness they experience, the more likely that you're going to have a fungal or possibly bacterial problem in that field. And you can use that leaf wetness calculation by monitoring the relative humidity in order to plan your sprays for certain fungicides and things like that. So again, very important. We use relative humidity also to help estimate water loss in the field. It's a big important piece. Temperature, wind, and humidity are some of the most important things that cause water loss in the field. And when I go to irrigate, what do I need to know? How much water do I estimate left the field so I know how much I have to put back when I irrigate? Again, lots of important considerations to know these things. So let's take a brief break and I'll be right